Yeah. Okay. Yeah. So let me share my screen. And in today's technical session, we'll be seeing the fundamental, mainly the concepts of polarography. And we'll build on the concepts of polarography and how it differs from conventional voltammetry, which we have been seeing for a while now, and how does it is advantageous to have a polarogram over a voltammogram, and how this polarography paved ways to develop advanced voltammetric techniques like square wave voltammetry, DPV, differential pulse voltammetry, and there are so many other advanced voltammetric technique which basically avoids the issues that are commonly faced in simple voltammetric like transient LSV and CV. So we'll see one by one, and it is very important to understand polarography first in order to understand all these advanced voltammetric techniques. Then we can discuss about the same uh, in using them in different fields of energy conversion electrocatalysis, as well as in sensors and battery studies. Okay, so let's start with today's topic, polarography. You could have all studied about this topic in your masters, because and there is no electrochemistry curriculum in chemistry masters course in India or any other country, I guess, without introducing polarography, because polarography is what earned this man, Perovsky, the Nobel Prize for his invention of dropping mercury electrode and polarography, which he termed as polarography. Okay, so polarography principally is nothing but a simple voltammetric technique in which dropping mercury electrode or hanging mercury drop electrode is used as the working electrode. So that is the only difference between the conventional voltammetric, what we have been seeing, and the polarography. Okay, it is called polarography or DC polarography because the inventor called it so. He wanted to show a different name, because previously the voltammetry was known, but the main reason why he developed this mercury dropping mercury electrode is to study the surface tension of mercury, specifically in different solvent. So he wanted to check the surface tension and how the surface tension varies with the dielectric constant of the medium, and how does the relationship between the dielectric constant of the medium and surface tension of the mercury drop affects the critical mass of the mercury drop before it falls off the capillary. So these were the objectives for which he developed this technique, but during which he observed that this technique can also be combined with an electro active species, particularly for reduction, and it can be used to study the electrochemical reduction property of various analytes in the solution, because the mercury electrode is the only electrode which has the highest hydrogen over potential, which means that the hydrogen evolution reaction on Hg electrode is not at all supported because of the liquid metal characteristics, because hydrogen evolution requires a firm metal surface in which the metal hydride bond is to be formed. Moreover, the hydrogen and Hg bond strength is so weak that the hydrogen adsorption could never occur on hydrogen, Hg surface at ordinary conditions, or at the negative potentials at which all the other metals can perform hydrogen evolution reaction. So this has become so advantageous that people were able to study the reduction of alkali metal ions and alkaline earth metal ions like sodium, potassium, rubidium, and on the other side magnesium, calcium. These metal ions can never be reduced to its metallic state, to their metallic states in aqueous solution, because we know that the hydrogen evolution reaction will be predominant, and it will be selected over the reduction of alkali metal ion, and it will always result in the formation of an alkali. So that is why those metals got their name as alkali and alkaline earth metals, because in aqueous electrolysis, these metal can never be recovered as an in their elemental state, like metallic sodium or metallic potassium. But with mercury, it is possible to reduce them selectively without even starting hydrogen evolution reaction. But the beauty of another beauty of mercury here is that when these alkali metal ions and other highly reactive metal ions are, highly ions of the highly reactive metals are reduced on the surface of mercury, they form a solid solution in the liquid state, because the mercury is in liquid state. So they form an amalgam, which we have learned in our school days. So it basically gives us a way to study the electrochemical reduction properties of metal ions that cannot be studied with any other electrode. So that is the most beautiful thing about the mercury dropping mercury electrode, or in general mercury electrode. Okay, so the purpose of inventing this dropping mercury electrode was different, but the ultimate application in which it was found to be useful later was even better than what it was intended to do. So that is why Professor Herosky got the Nobel Prize for the development of dropping mercury electrode and the use of the same in polarography. Okay, so with that introduction, let's see. Just a moment, yeah. So what you see here is the standard diagram of dropping mercury electrode, in which we have uh, a tube which is connected to a capillary, and this tube is what holding the mercury, and there is also the mercury reservoir here kept in a mercury bulb. So just by adjusting the mechanic valves here, we can adjust the flow or rate of flow of mercury, that is forming a Hg bulb, or what we can say Hg spherical electrode or drop. Okay, so this drop can be stabilized without falling just by stopping the flow of mercury here. In that case, it is called hanging mercury drop electrode or static mercury drop electrode. Okay, so this mercury drop is then subjected to perform the reduction of metal ions that are impossible to be reduced with any other electrodes because of competitive hydrogen evolution reaction, which is not an issue with the Hg electrode. Okay, so typically the diameter of this mercury drop is usually 1 millimeter, but the internal diameter of the capillary is very less, usually on the order of 5 into 10 to the power minus 3 centimeters. So that makes makes it possible to make very closely or nearly spherical electrode, which is not possible with any other metal. Okay, so the spherical electrode is very important in electrochemistry, because all the other knowledges we have ever gained in electrochemistry before were only occurred with the planar electrodes or disc electrodes, which have parallel diffusion. Only the diffusion layer growth and the diffusion of electroactive species from only one direction, right? But with the spherical electrode, we have the diffusion layer formation all around the spherical electrode. I mean, nearly 360-degree angle flow of electroactive species through diffusion. So, which is something which, that have not been observed before with the conventional planar electrode. And for addressing this diffusion phenomena, spherical diffusion phenomena, there was this famous equation, Ilkovic equation, which was derived to understand the spherical diffusion layer formation and the diffusion of electroactive species in that spherical depletion layer of electroactive species in electrolyte solution. So these are something that you need to know why the invention of DME led to a Nobel Prize. Okay, so the principle is very simple, as I introduced earlier. It is a voltammetric technique with the DME or HMDE as the working electrode. Okay, the salient features are the IV curve is highly reproducible. If you take any other electrode in electrochemistry, if you perform the voltammetric analysis. Even with the same electrode, the next instant you will not get the same IV response. There will always be some difference between the first run and the second run. It is because of various reasons. One is that the surface will get poisoned, or the surface may have been chemically changed because of the first cycle of electrochemical reaction, or there could have been significant depletion of electroactive species in the interface, and the double layer could have also grown thicker, which makes the diffusion of electroactive species to the electrode surface even more difficult, so that the IV curves with the static planar electrode or disc electrode are never reproducible. But with the mercury drop electrode, what we are doing is that we have a fresh mercury drop in which the diffusion layer is spherical, and we analyze the electrochemical property, and the mercury drop is let to fall down. So when it falls off the capillary tube, what it does is that it also stirs the solution around it, so that the diffusion layer or the depletion region, whatever created by the previous mercury drop electrode, is actually replenished with the fresh electrolyte solution. So every time a mercury drop forms, there is always a fresh solution, and there is always a fresh metallic surface, and there is no depletion layer. So every time the IV curve, whatever you see with the mercury drop electrode or dropping mercury electrode, is highly reproducible. And yeah, because of the reason I told, the electrode surface is fresh, and the spherical double layer is renewed at each drop. The second thing is that it has very high hydrogen ore potential. So that is very, very important. And because of that, we are able to study the electrochemical reduction properties of many metal ions that are impossible to be reduced in aqueous solution. So these are the salient features of dropping mercury electrode or mercury drop electrode. So the issues with the Hg is that it is easily oxidized to Hg plus and Hg 2 plus, which means that you cannot use mercury drop electrode or dropping mercury electrode to study the oxidation of electroactive species. So it is mainly only for reduction, because in neutral medium, this mercury oxidizes at potential of 0.2 volt versus SCE, which means that there are not enough electroactive species that can be oxidized within this potential, and that can be studied using this electrode. But when you look at the cathodic potential window, it is enormous or humongous, I would say. So you will literally cover everything except lithium, because lithium is the only metal which is having very high stated electrode potential to be reduced, and within that potential window, there are some amount of or some selectivity towards HER even with mercury electrode, but still it is possible to reduce lithium in the presence of mercury. And it is highly toxic, we all know that, and also carcinogenic, can cause cancer. And to clean the drop or spillover, which is inevitable when we use dropping mercury electrode, needs zinc powder to make amalgam of zinc and mercury, and then subsequent dissolution in acid like nitric acid or sulfuric acid, which are hazardous processes. And when one continues to work with mercury drop for a while, be it a female or a male mammal, not only human being, but every mammal will have increased danger of losing their fertility. So these are something that we need to worry. And the main thing that can lead to this issue is that its volatility, because mercury is slightly volatile, and that volatile mercury can be easily inhaled even without our knowledge. So it is highly dangerous metal to work with. On the other side, this is the typical cell setup for a dropping mercury electrode equipped as a working electrode here. As you can see here, there is the mercury bulb, which is having the mercury backup. And using this wall, we can actually control the flow of the mercury that is flowing down the capillary tube to form the mercury drop. And this drop's lifetime is very important, because uh, the lifetime of the mercury drop is what determines how long we can use that mercury drop's surface for the electrochemical reaction we are studying. Okay, that can be varied from 0.5 to 10 seconds depending on the flow rate what we are going to set, but it is impossible to vary uh, beyond this. Even if you open the wall fully, because of its high viscosity, the drop will not form immediately, and the lifetime will be at least 0.5 seconds. But even if you set it at the very low flow rate, you can maximum extend up to 10 seconds, because beyond which, even if you reduce the flow rate, still the flow will be stopped, and you will be having static mercury drop electrode or hanging mercury drop electrode, not the dropping mercury electrode. So this is one of the main limitations what we have with dropping mercury electrode. And the critical radius of mercury drop is 0.5 millimeter. So it means that you will not have a larger electrode surface area in order to study the spherical diffusion layer of larger thickness. The major disadvantages is that as the drop grows, mercury drop grows at the tip of the capillary tube, the surface area of the mercury drop is also keep on growing, which means that the area is keep on increasing even when you set the same potential. Suppose assume that you are performing a chronoamperometry experiment with a mercury drop electrode. So initially the mercury drop is smaller, so that the area is also smaller. You observe small current, but when the drop size increases, the area is also increasing, so that you will see larger currents. So okay, with the changing surface area, you will see increasing current. Not only that, when the surface area changes, the double layer, so, I mean the thickness of the double layer or size of the double layer is also changing, which means that when the double layer size changes, charging of the double layer, continuous charging of the double layer is inevitable, which is which is in sharp contrast with the voltammetry technique. In voltammetry, we see that when you perform chronoamperometry with the planar electrode, static electrode, you will see the capacitance current flowing for a few milliseconds to 1 or 2 seconds only. But later it will be completely diminished, and whatever we observe after that point of time will be of our reaction of interest. So in this case, it is not so. Because of the growing mercury drop and the changing surface area, the double layer size is also increasing. So when does it happen? When does it happen? The charging of double layer, I mean the continuous charging of double layer, is inevitable, and that will also impart a huge background current. So the current correction is very important in dropping mercury electrode having electrochemical cells. Okay, so to overcome these advantages, what people done was that they simply replaced DME with HMDE. HMDE is nothing but a hanging mercury drop electrode, which is also known as static mercury drop electrode. So in this case, the mercury drop is not growing, but it is still spherical, so that we will have a spherical diffusion, and we can study the spherical diffusion phenomena of various electroactive species in the solution. And also it enjoys the high hydrogen over potential characteristic of mercury. But disadvantages is that it is having some similar properties to that of conventional voltammetric techniques, in which static, planar, and disc electrodes are used. The surface is not renewed, and the depletion layer is not overcome, because in dropping mercury electrode, when the mercury drop falls down, it actually stills the solution around it, and the depletion layer is actually disturbed, and the electrolyte and electroactive species near the capillary tube or the tip of the capillary tube is replenished with the concentration of the same concentration, nearly the same concentration as that of the bulk with the electroactive species. But since we are just hanging a mercury drop, and we are not letting it to fall, it is not overcoming the issues that are associated with depletion layer, which is very common in conventional voltammetry. So it is just a spherical static electrode with a very high hydrogen over potential. So you can study all the reductions with no issues of ever increasing surface area and a huge background current contribution. So this is the advantages. These are the advantages of HMDE over DME. So now I think we have exceeded 15 minutes. Let me check. Yes, more than 15 minutes. Then we'll from next week we'll see the effect of diffusion limitation and on static and transient techniques. in polarography using both the DME as well as HMDE. So with that, I would stop here and move on to the questions I have received. Just a moment, yeah. Mm. So as always, I will not say the name who asked the question to maintain the anonymity, and anonymity, and also, uh, yeah, some of those who asked these questions are not available online today because of their time conflicts. Some of them are in the Americas and also in Europe, so they couldn't join. So they will be able to get their answer when we upload this session to YouTube. So let's start with the first question. I have a question related to electrocatalytic activity. For the redox system, how can the electrocatalytic activity of the materials can be defined? Sometimes the electrocatalysts show lower potential and high current density in the irreversible system, but in the reversible system, the same catalyst fails to achieve both low over potential and high current density at the same time, or only achieves high current density. What is the reason for these differences? The reason for these differences is that the reversible system and irreversible system, what you are studying, are not the same. So because you would expect a catalyst to perform with a similar activity towards the same reaction, so not for different reaction. For example, we can have several examples for that. For example, let's take platinum. Platinum is a wonderful catalyst for hydrogen evolution reaction and also for oxygen reduction reaction. But if you use the same catalyst for oxygen evolution reaction, it is not performing well because of its unfavorable energies of interactions with the respective intermediates. So that is the reason. Because it is obvious that when you use the same catalyst for two different systems, in which one is reversible and another one is irreversible, obviously that means that they are two different analytes. So with each analyte, a catalyst surface will have its own adsorption and desorption characteristics and the corresponding free energies of adsorption. So if the Sabatier principle is not fulfilled by your catalyst, I mean, having a moderate adsorption free energy and being with the density of states, particularly for reduction reaction, I mean, probable, optimal density of states, your catalyst cannot behave in the same way. So the moment you change the analyte, you must not expect your electrode to behave in the same way, because it is not that a catalyst which is good for a particular reaction should also be good for some other reaction. So we should not expect a catalyst to behave in such a way. The second question, what is the difference between TEFL polarization curve and TEFL slope? TEFL polarization curve is nothing but the plot which we construct using current potential data, which can be obtained from chronometry or very commonly used transient technique, although it is not a correct way of forming a TEFL polarization curve, is a plot in which log current density is plotted against the over potential, IR drop free over potential. The slope is something we get from the linear line of this TEFL polarization curve. So that is the difference between these two. And does changing the distance between the electrodes in three and two electrode system change the amount of materials deposited on the electrodes? No, never. Because the amount of material deposited on the electrode will never change with the distance, because you are just adjusting the position of your electrodes in the electrolyte solution, which means that the electrolytic resistance, I mean the solution resistance, may vary if your electroactive species is very low in concentration, or the conductivity of your electrolyte is comparatively poorer. But for reactions that I am doing, I am interested, like OER and HCR, the analyte concentration is always high, like 0.5 molar H2SO4 and 1 molar KOH, in which pH is 0 and 14, and I have abundant ionic species in the solution. So I do not have to worry about the solution resistance. In those cases, even when you place the electrodes working on the reference electrode at a different position, that will not affect the activity. But the amount of material deposited on the electrode will never change depending on the distance between the electrodes inserted in the electrolyte solution. So let's go to the next question. which is correct, to use the number of moles of catalyst or the number of catalytic sites in the electrode for the TOF calculation. Both are correct, given that you are using the appropriate equation. If you are going to use the number of moles of catalyst in the denominator, you don't have to use the Avogadro coefficient or the constant on the upper part of your equation, nominator. I think, I don't know the name. So you just have to keep your current density. But when you want to use the exact number of catalytic sites, you need to use the Avogadro constant over the dividing mark, because you want to obviously convert the number of catalytic sites into number of moles, which can be attained by doing this. Let's move on to the next question. What type of electrode can be used to avoid huge IR drop issue, and why? Can serial measurements be taken directly as XA? Yes, I mean XA, sorry. Yes, that's a very good question. Because type of electrode can also impart huge IR drop. If the conductivity of the electrode, I mean electronic conductivity of the electrode is poorer, there will be huge uncompensated resistance. And if the dimension of the electrode is 3D and highly porous or so rough, and the double layer thickness is so high, so that it also takes up longer time to charge the double layer, there will be huge potential delay that will ultimately result in huge IR drop. So usually smaller electrode of tiny surface area, probably a smoother surface area will help you to avoid huge IR drop issues that are mainly coming from your electrode. But in general, IR drop is mainly from the solution part, and particularly from the solution resistance. So if your electrode is highly conductive, even if it is 3D or highly porous or highly roughened surface, you don't have to worry about that. If you are having a good electrolyte with appreciable electrolytic conductivity. And can serial measurements can be taken directly as EXA? And yes, EXA, I assume that you have asked electrochemical surface area. If you are talking about electrochemical surface area, yes, you can take serial measurement after normalizing CDL with its specific capacitance. But you should be reminded of the fact that the CES value, I mean the specific capacitance what you are going to use to normalize this double layer capacitance, should have been the one which you determined yourself for your material. So in that case, you can take it directly as an EXA. But if you are talking about electrocatalytically active sites, which I often term as ECAS, no, it cannot be taken, because the serial measurements are done using non-Faraday consumption desorption currents, right? So that there was no, or there is no electron transfer, so that cannot be directly taken as an electrocatalytically active site. Okay, so but it can be taken as electrochemical surface area, given that you are normalizing the CDL with the double specific capacitor which you determined yourself for your material. Yes. Determining electrocatalytic activity in determining electrocatalytic activity, how much is the contribution from background currents usually, and what are the factors governing it? This is a wonderful question. As I told in relationship with the question about the IR drop, if your electrode is highly roughened or porous and 3D, I mean any electrode in which you have the probability of having a big double layer. Okay, I mean double layer that is larger in area, that will take up huge time in order to charge up the double layer, because without charging the double layer you can never perform electron transfer across the interface. So when you have a large electrode and a large double layer, this will usually has huge potential delay, and also what I can say, affect your electrocatalytic activity. Yeah, and in those cases, the background currents are usually higher than what we usually see with the planar smooth electrodes. Yes. How to decide whether a catalyst is suitable for HCr or OER in acid or alkaline medium? What are the qualities of a good electrocatalyst? I have been discussing these things in all my reviews. Almost all the reviews I have published in recent years, I have been discussing these things with all the new advancement made in this field. And the main thing I always suggest people to do is that first do a quick literature survey whether the material what you are having in your hand is used for HER or OER, and if it is already used, how is it? How was it? Its performance, and whether it was comparable to the state of the art, or can it be tuned structurally or electronically to make it to be the state of the art. These are the things which you usually do. But even before doing all these things, the very first thing one must do is that first go check the Borbach's diagram of each element that your catalyst has. Suppose if you are having some material like say sodium vanadium phosphate, and you want to use this material for HCr or OER, please check the Borbach's diagram of sodium, vanadium, and phosphorus, and you will understand at which pH and at which potential condition this material can be stable. Whether at this potential condition, from Borbach's diagram, you will understand at which potential condition and at which pH all these three elements can be stable and can be stiff without losing their integrity, structural integrity, so that it can be used and in that particular condition for your reaction of interest. This is the first thing. The second thing is that fulfilling the Sabatier principle, you need to check the adsorption free energy values. Like if you're having vanadium and you're willing to use it for OER, check the oxygen adsorption free energy value, hydroxide adsorption free energy value, and hydroperoxide intermediate adsorption free energy values, and compare these values with other known OER catalysts like nickel iron oxide hydroxide, nickel hydroxide, cobalt hydroxide in the first row. So if you are having a comparable value with this thing, you are good to go with the OER application in the pH in which you have found out that it can be stable from looking at the Borbach's diagram. So these are the two things one must do. And about the quality of good electrocatalyst is nothing but the problem is simple. You need to have an active catalyst that is highly selective for the reaction what you are willing to study, and also being very stable. So these are the three qualities that a good electrocatalyst should have. So yes, that's all about the question. And yeah, now my supervisor told me to work on hydrogen production through water splitting. I'm not familiar about electrochemistry. I'm a little confused where to start. What characterization needed to check the property if I synthesized different nanomaterials for this. Yes, yeah. So actually, this question is also answered with my previous answer. So whatever material you have, first check the Borbach's diagram, then you go do search on the adsorption free energy values, then you perform the reaction if you are satisfied with these two steps. So this is the actual way one should work. So you don't have to worry about that. In order to understand the type of analytical tools you must use for electrocatalytic HCr and photoelectrocatalytic HCr, there are many reviews in the literature, even for just for the experimentation. So you can refer those reviews, and if you still have any doubts in understanding the concept of the electroanalytical tools and how it is used, you can be specific about your problem, the problem you're facing in using a particular tool. Okay, so I'll be happy to help you in that case. Yes, I think that's all. Let me just stop sharing the screen. Let's go back to the room. Yeah. Thank you very much. Yeah, Marudu Pontian is here for all the session, and I'm very happy, Thambi, you have raised your hand today. If you're a host, please unmute and ask your question. Marudu? Subhas, could you please make him as a host?
Yeah, he's a host now.
Okay. Marudu, are you there? Okay. Yeah, I think he might be having some issues. Yeah. Yeah, if anyone else of you having anything to ask, you can raise your hands. Yes, Dr. Mowli.
Hi.
Yeah.
Good evening for you.
Good evening.
Well, the first question is about in the last session from your side, you have told that if we are doing a TOEFL plot, we should try to see for noble metals, at least you take a potential which is over potential of above 50 millivolts. considering kind of multi-electron transfer process possible things.
Yes, exactly.
If the plot that you have for a noble metal electrocatalyst, and you have a huge disturbance in the signal after, let us say, reaching 50 millivolts, in that aspect, what you suggest, like you reach almost like, let us say, 200 to 300 milliamps of current density, and then you cannot get kind of points that are following each other in a sequential manner. In that case, what you suggest?
Yeah. So the noise, what you're seeing when the current density increases, is because of the gas bubbles formation, particularly for HCR. And you can avoid this just by ensuring the swift removal of gas bubbles, which is usually done by performing the reaction using RDE. So at 1600 RPM or something, or you can also stir the solution. But very recently it is understood that stirring the solution with a magnetic pellet can also cause disturbance on the electrocatalytic activity of many metals, including PT. So I would advise you to perform the reaction with the RDE, so to avoid this noise issue. If you are still having if you are still having similar issue, you can also try increasing the electrode surface, because when you have a larger electrode surface, the impact of the gas bubble forming and masking your catalytic sites will be relatively less when you have a smaller electrode, okay, when compared to the instant where you have a smaller electrode.
Okay, well, I am working with the supported electrocatalyst stuff,
Okay, then
so I
should not
cannot
be.
go for RDE. And then stirring part, okay, I am avoiding that thing in recent times for different reasons. So you suggest, like, is it okay if you try to take let us say over potential windows of 10 to 20, 20 to 30, 30 to 40, and 40 to 50, and then you try to give an overview of TEFL slope over there,
Yes,
and
yes,
then
yes. It is
comment
absolutely fine.
on it's fine like that also.
Yeah, it is absolutely
Okay.
fine. Yeah, usually in the noise, what you are witnessing with the high current density is seen mainly in voltammetry, transient voltammetry, like LSEChem, because we are not letting the system to stay at a single potential for a sufficiently longer time, and when we switch the potential immediately, even before the gas bubble which was formed in the previous potential step is not removed. So we are actually skipping a potential step and not letting the catalyst to measure the activity in that particular step. That is the reason why we see the noise. So if you are completely avoiding the use of LSV and performing chronoperimetry, like for constructing SCV, sample current voltammetry, in which you are going to set different potentials, like 10 millivolt, 12 millivolt, 30 millivolt, like that, you can increase the potential in chronoperimetry and perform the reaction for 100 seconds. That is enough. Within this 100 seconds, your interface will be stabilized, and there will also be an equilibrated gas bubble removal and electrocatalytic activity. In that case, the noise is usually minimal. So you can have a better understanding of your interface on the set potential, and you can perform a airdrop correction later, and you can also construct a TEFL plot which is free from these noises. So that is another option.
Okay, thank you. In the past session, you have told normalization of EIS, and then basically the fundamental of EIS, where you have a solution resistance that is inherent to the solution rather than the electrode. But in EIS, after you normalize, your internal resistance has jumped to, let us say, 3 folds. So how do you justify this point?
No. The normalization in EAS is that we are not dividing it, so it will not increase. We are actually multiplying it, right? So, for example, if your area is smaller,
True,
Okay.
true. But changing of internal resistance by changing the area, let us say, internal resistance should not affect.
That is true. Yeah, that is true. That is
But
true.
but in the paper of GMCA, the internal resistance
Yeah.
that the EIS is showing, it's quite very different. Like you have 2-3 ohms of difference.
Yeah.
So
That is because of normalization. Yeah, that is because of normalization, and that is to be used when you are using a normalized activity for IR correction, because you perform your reaction with an electrode which is having an area lesser than 1 centimeter square, and you are also having a resistance value which is obtained for an electrode which is having a same area, I mean lesser than 1 centimeter square, but you want to use the same resistance for an activity which is actually normalized to make the observed activity to be for 1 centimeter square. That is actually wrong. So you cannot do that. So when you want to do that, you should also normalize your resistance. So that is the theme there. So when when you want to when you want to perform IR drop correction with a normalized activity, you should use normalized resistance. In that case, it is called resistivity because it is resistance per centimeter square. So in 1 centimeter square area of electrode. So that is resistivity. When you have a normalized activity in current density, you should use resistivity. When you have just current, you should use the resistance. So this is the difference.
Oh, okay. Yeah. And then in last question, sorry.
Yeah.
In kind of measurements it's like maybe not important question, but when you take the scale, like let us say milliamps or microamps or amperes, automatically when you consider to evaluate the area under the curve, it will be given basing on the unit that you take. A milliamp, it will be like a millicoulomb, or it is always coulomb?
No. Like you said, it will be millicoulombs. For example, if you are having a current density scale in milliampere per centimeter square, and in volt, what you have in area is that it is milliampere into volt, right? So you will have to divide this area by its scan rate in order to get your charge. So because scan rate has the unit of millivolt per second or volt per second, so the volt what will get cancelled, and the per second what you have in the denominator will go up the equation, and it will become either milliampere second or ampere second, depending on the current unit, what current density unit what you had in your y-axis. So if it is milliampere second, it will be millicoulombs. If it is ampere second, it will be coulombs. So it is just like that.
Okay, thank you very much.
Yeah, thank you, Dr. Mowli. Yes, Dr. Maruthu Pandian, if you are available now, please unmute. I can see that you are already unmuted. Yeah, yes, Thanvi, please go.
Yes, no.
Yeah.
I
cannot hear you. I cannot hear you loudly. Can you please be? Yeah, please.
Anna, can you? In your
yeah. You are now. Yeah, you are now. Yeah.
The third question: does the changing the distance between the electrode in the 3 electrode or 2 electrode mode? Anna, whether
yes,
the system is affect that amount of material deposited or not? Anna?
Oh, okay. The amount. So this question is related to. Oh, this question is related to electrode deposition.
Yeah, yes, Anna. Yeah.
Oh, okay. Thank you, Maruthu. I thought that it is related to the loading of the catalyst, loaded amount of the catalyst. Okay. Yeah, thank you for pointing out, Maruthu. Thank you very much. Yes. Yes.
Anna?
If it is electrode deposition, it will definitely affect. Yes.
Yeah, yes, Anna. For remind you only, I came.
Yes. Thank you, Maruthu. Yes. I thought it was for the loading of the catalyst. Yes.
Okay.
Yes. Thank you, Maruthu.
Okay. Yeah. Thank you, Anna.
So yeah, if any of you have any other question, I can see there is a question in the chat box. How to determine the specific capacitance of the material of our interest? There are two ways. You can perform CV, and there is in all supercapacitor paper you have the respective equation for calculating specific capacitance for any material. But as you know, cyclic voltammogram always exaggerate the capacitance value, specific capacitance value. The best way, because of the issues, IR drop issues, and double layer charging, what we are witnessing, you should always go for galvanostatic charge discharge, which is free from IR gap, because in this case GCD, we are not controlling the potential of the interface. Instead, we are just monitoring the potential. We are just observing with respect to time in GCD. So the specific capacitance determined from GCD can be used for calculating your EXA, which you will obviously do by normalizing the double layer capacitance, which you have determined using CV. So that's how you need to do. And for calculating CS from GCD, there are a lot of reports in the literature, and it is very famous. Anybody who works in supercapacitor will help you to do that. It is very simple. Yes. Yeah.
Can I ask you one question?
Yes, Dr. Mohli. Yes, please.
Do we have any reference literature that did for platinum above 50 millivolts for Tafel slope and provided a value of 30 millivolts per decade?
I could not remember anything specifically for that, but there are instances where I have seen papers in which more than 3 decades of current densities are covered with platinum electrode and just gave Tafel slope, an average Tafel slope of just 32 to 35 millivolt per decade. So if I stumble upon something, a paper like what you have asked, I will email you.
In one of your recent paper of let us say 2020, I think so, where you have done for HER,
okay,
and you have used platinum as a kind of reference one, and there your Tafel slopes of platinum were around 40 to 60 maybe. I don't recollect that word properly.
Yeah, maybe.
So maybe that means like will reviewer ask you a question that why don't you try to do something more about platinum, as every platinum should work very good?
No, that we cannot do, because as in the technical session I told, you cannot get the reproducible IV curve, not only IV curve, not even Tafel polarization curve with a planar static electrode, because of so many reasons, even for the very easily doable HCR. Okay, there are many reasons why we cannot do, and it is not that since platinum is the good material, it should always give the lowest ore potential. Many things can affect the kinetics, its surface and its roughness and crystallinity, the faceting, or if it is amorphous. There are so many other things that can affect the kinetics. So the Tafel slope is merely an indication, indirect indicator of the kinetics, right? So it is actually, I would say, that unwise to expect the same Tafel slope with all PT. So that is not possible actually. But it is also not rare to see Tafel slope values of 90 millivolt per decade, 120 millivolt per decade with platinum, particularly in alkaline medium, because there it has to perform the water dissociation along with hydrogen adsorption, the first step, water dissociation coupled Wolmer reaction. So it does not mean that since you have platinum, you need to always show lower Tafel slope. You can show a higher Tafel slope, and you can justify when the reviewer asks.
Okay, and when you are working with HER electrocatalyst,
yes,
let us say you, as the theory says, like the current should start from zero, but as other way of seeing all discussions, we see that as you say, the to develop that space charge region and then to cross the charge from the space charge, this also increases the capacitance. So you can see a capacitance current. So how do you counter this thing when you are writing a paper?
Yes. And in HCR, you don't have to worry about the double layer charging, because hydrogen evolution, or hydrogen reduction on platinum actually occurs before the reversible potential, and that is what we call hydrogen under potential deposition, right? So this hydrogen under potential deposition actually paves way for immediate evolution of hydrogen at its reversible over potential. That is what we call hydrogen over potential deposition. So it is for HCl. In other cases where this is not the case, you have a large background current or capacitance current, it is always wise to perform the studies with an electrode of lesser area and have an electrolyte which is good in conductivity and highly abundant in electrolytes, I mean non-participating inert electrolytes, so that we will not have issues in charging of the double layer with a longer time. So these are something that we can do.
Okay, understood. Okay, thank you.
Yeah, thank you, Dr. Mowli. Yes, Dr. Sekhar, if you are a host, unmute, ask your question. Sekhar?
Hello.
Yes.
I'm
Yeah, I know.
I'm not an electrochemist, and I'm afraid to ask. Maybe my question may be sometimes it may be wrong also, but I want to know one simple question related to sensing field.
Okay.
So there is usually people do sensing like electrochemical sensing as well as photoluminescent sensing. Is there any means in photoluminescent sensing also the mechanism may be due to electron transfer? So some kind of mechanism will undergo due to electron transfer, and in is that possible to correlate electrochemical sensor and photochemical sensor? I mean, we can confirm whether we can confirm the process occurs only due to electron transfer by electrochemical method, means electrochemical characterization, because they people people who are publishing in field of photofunctional materials, they are not showing any kind of electrochemical characterization to confirm. Instead they do some like lifetime analysis, which is not showing exact mechanism, since it may be due to other sort of other sort of reason also. So is that possible to confirm by this electrochemical method?
Yes. Thank you, Dr. Sekhar. Yeah. I'll answer your question. Would you please put your mic on mute? Yeah, thank you. Yes. Photoluminescent sensor, as you have pointed out, is based on the can also be based on the electron transfer that is occurring when we irradiate the material, photofunctional material, with a suitable wavelength of light, where there is always excitation and relaxation, and all these things can come in the form of luminescence, and that we use the luminescent intensity is what we use to detect an analyte, because it can be done in two different ways. An analyte can enhance the luminescence, or there are analytes that can quench the luminescence, so that from the flux variation one can easily determine the amount of the analyte. So this is the fundamental principles in photoluminescent sensors. In electrochemical sensor, what we have is we have an electrocatalyst which is having appropriate energies of interaction with the analyte, what we are trying to study, and we apply a specific potential. And since the potential at the applied potential, at any applied potential, the current is directly related to the concentration of the analyte as per Nernst equation, we actually can calculate the amount of analyte in the solution depending on the current and with varying concentration. So these are the two fundamental basic principles of photoluminescent sensors, luminescent sensor and electrochemical sensor. I see a way in which these two can be connected, since the mechanism by which the analyte is sensed is different with these two areas. The material which is used in photoluminescent sensor can still be studied and using electrochemistry to get important information such as the band gap. And yes, band gap is the main thing which you can find out by simply performing a cyclic voltammogram at the lowest standard possible in an electrolyte which is totally inert, and there is no parasitic reaction. So in that case, the oxidation and reduction peak potential differences can be directly considered as its band gap. So this band gap can also be compared with the band gap which you determine using the tau plot in DRS for solid materials and from UV visible spectroscopy for easily dispersible materials. And you can compare the band gap value that you determined using tau plot and the electrochemical characterization, and you can make a discussion out of these two same. But I really do not see how these two sensors can be interconnected, because the mechanism by which analyte is sensed in electrochemical sensor is purely by electrooxidation, in which the electron transfer occurs. But in photoluminescent sensor, it is the excitation and relaxation, and during which the luminescence is observed using the luxometer. So I don't see how these two can be connected. So other than we studying the band gap of the photoluminescent material. Yes.
Hari?
Yes, Dr. Moli, I have another question in the chat box. Let me first answer that, and I'll come back to you. And yeah, it's Srividya. In the case of transition metals-based catalyst for OER, mostly self-oxidizing peak is observed. Yes, means the catalyst has undergone oxidation. So after some point of time, most of our catalyst will be oxidized, and eventually it will run out. It will worn out. In such cases, how can we claim the stability of our catalyst? Will turnover number be a good indicator of this? Does this mean a lesser self-oxidation peak would mean a stable catalyst? But on the other hand, this would mean that there are fewer active sites. Yes. You must understand one thing, that yes, it is true that your catalyst must oxidize before it can perform OER. But at the end of evolving a molecule of high oxygen, the oxidized catalytic site is coming back to its original oxidation state. It is not like they are staying in the higher oxidation state forever. So if you see the mechanism of OER with all the materials, you will see when the adsorption of hydroxide ion occurs, it also takes up an electron to form metal oxide intermediate, and that forms another metal hydroperoxide intermediate, and then it evolves oxygen. So when it evolves oxygen, the metal which got oxidized in the first step come back to its original state. So it is like a cyclic process. So you will never run out of catalytic sites that are in the appropriate oxidation state for OER. So you don't have to worry about that. Yes, it is still turnover number. I would say turnover frequency is still the good indicator of activity, because if you know the number of active sites that are participating in the OER, it is always good to show your activity in terms of TOF. And on the other hand, the oxidation peak, what we see is what telling us the number of active sites that is actually participating in the reaction. Okay, so when you have a lesser oxidation current, which means that you have a lesser number of active sites participating in the reaction, there could be lesser OER or HR, lesser OER current. So obviously, a higher oxidation peak current means there is a higher number of active sites, but it does not mean that not all the highly active catalysts should have a higher oxidation peak. For example, if you take nickel iron LDH, for example, nickel iron oxyhydroxide, the oxidation peak is suppressed in the presence of, the oxidation peak of nickel is suppressed in the presence of Fe, and the redox shuttle that is actually involving in OER here is nickel 4+ and nickel 3+. So there is no role of nickel 2+. So when you don't have nickel 2+, you will not obviously see a nickel oxyhydroxide formation peak. You may see something in the very first cycle, but from the next cycle, it will be nickel 4 and nickel 3 couple, which is performing this reaction. And there are also speculations that it is the iron 4 and iron 3 couple which is performing the reaction, but it is still not resolved whether the Fe is the active site or the nickel is the active site. But when we have both, the activity of OER is very high when compared to all the other metal catalysts what we have for alkaline OER. So you don't have to worry about basically the oxidation peak current. If you have a large peak current, it means that your catalyst is having a higher number of accessible sites. Okay, and that will never run out, because number of active sites that are oxidized to a higher state will eventually have to come back to its original state at the end of evolving an oxygen molecule. So yeah, that's it. For Chavan, can we have a session on career development. Yes, Mr. Chavan, you have been asking this for a while, and we'll be having. Yeah, thank you, Srividya. And I also have an important announcement. I'll be visiting a few of my collaborators in India during May first week to the first week of June, and I have been asked to host a 2-day summer school on energy conversion electrocatalysis. It will not be something like what we are doing now. So I want to give hands-on training for 20 to 25 doctoral students who are interested in energy conversion electrocatalysis. We will not be talking about the theory and the things what are going on. It will not be a school, summer school that is kind of boring. Instead, it will be like engaging. I want to teach you how to do the electrode modification, how to polish the electrode, how to make a reference electrode by yourself, and how to calibrate your reference electrode, and what are the things you need to consider when you choose a material, how to design an effective catalyst. These are some things that you will never find in any standard electrochemistry textbook. So these knowledges are accumulated through years and years of experience for people like us. So I want to share my knowledge with 20 to 25 selected students, doctoral students who are currently doing PhD in India during my visit in the month of May. And this event will be hosted by Manonmaniam Sundarnar University, Tirunelveli, at Department of Energy Chemistry. So if any of you are interested, the brochure will be out probably by the next week. Please do register and we'll meet in person. So it will be more effective. Yes, Dr. Mowli, you were about to ask.
Yes, sorry for consuming the time.
Yeah.
Already it's done.
Yeah.
In the textbooks, I see that copper has a specific potential window for getting dissolved or for being unstable. And then when we talk about doing UPD, I see from the paper saying that you try to keep your electrode at 1 volt versus RHE for a while so that you dissolve everything, whatever is there on the surface, which is of copper. And then you try to apply a potential of 0.3 to 0.25 or something like that. And then keep it for a while and then run LLSV. So the window that copper dissolves is like around from 0.4 to 0.6 or something like that.
Yes.
So what is that I'm missing here? Thank you.
Yeah, but you're not missing anything, because I advised a higher anodic potential to ensure that none of the copper is left behind in undissolved or in a metallic state. So you will ensure that there is no metallic copper on the surface. All the copper are already oxidized and they are in the ionic state, cupric ionic state in the solution. So when you perform the reduction again by setting a potential of 0.3 to 0.5, you'll ensure that the uniform monolayer of metallic copper is formed on a metal surface. So this monolayer can be stripped out of the surface by doing oxidation of the same, by simply performing an anodic LSV. So from the current of oxidation, we will quantify the amount of copper which is deposited on the surface, and we can also calculate the electrochemical surface area. So this is the idea. The idea of having a higher anodic potential is that to ensure that all copper are completely oxidized and dissolved into the solution. Yes.
Yeah, one question is that, what is this potential window where copper is unstable? What does that mean? From the textbooks, they say that copper is unstable or copper is, like in a potential window, it is not stable, they say.
Yeah.
What is this window?
Yeah, this window is where you witness the oxidation of copper and dissolving.
So this oxidation means dissolving, or what is that?
You are actually oxidizing copper, and where it loses electron and dissolves into the solution as its ion, like cupric ion.
So this dissolution happens only in the window of the peak that you see?
No, not only in the window, at any potential beyond that potential. Also at the potential where it is said to happen. Yes.
So why do they confirm the line saying that potential window copper is unstable.
Yeah. It is, I don't know why they intentionally wanted to say that thing. So, for example, suppose let's take these electrochemical reactions are not like the quantized reaction. You will not see a reaction if the amount of energy what you give is not exactly the same what is needed, right? So, for example, the electrolyzer experiment everyone performs on YouTube. All they do is that they take two graphite pencil and connect a 12-volt battery, and they see OER and HITCR. So it is just like that. Even though the potential window that is said to be the unstable window for copper is 0.4 to 0.6 volt, it does not mean that when you set 1 volt, the copper will not dissolve. It will still dissolve, and the rate of dissolution can even be higher because of the higher potential. So the meaning of this unstable potential window may be to let the reader know that this potential is sufficient to dissolve the copper anodically.
Okay, because like this is from the mother books of electrochemistry from the professor somewhere. So I was confused, like I was trying to find some literature, but I was unable to find this thing of understanding. That's all. And thank you for a previous explanation of my past question that I posted by mail.
Yeah.
You're saying something. Sorry, I disturbed you.
Yeah, no problem. It's my pleasure. And in fact, I'm doing it for my own benefits. I have been writing a monograph on the appropriate use of electroanalytical tools in energy conversion electrochemistry. So I was actually struggling a little bit earlier because I don't know the views or the problems faced by the researcher, and how do I get the discussion to be friendlier with the reader. So the main reason why I'm doing this thing is that the views I'm getting to know from all the stages of researcher is actually what is helping me to construct this monograph in an effective manner so that it will be engaging to all kinds of reader. So I'm actually doing it for my own benefit, and also thank you very much for joining every week and sharing your views. Yes, thank you. We have a question from Mr. Manoj. Yeah, thank you, Dr. Mowgli. Looks impressive about summer school, whether it will be open also for postdoctoral students, any possibilities. Actually, that I need to consult with the organizers. They said doctoral students will be most interested, but I don't see why postdocs cannot participate. So there is no reason why we would want to limit, but it may depend on the number of participants showing interest. So you may, I'll just confirm with the organizers. Yes. Maybe if you can join the next week, I will update you with that. Or even if the brochure is out before that, I will circulate, and all the details you may need will be there. And but I know one thing for certain, that there will not be more than 25 students. So yes, within that 25 students, we'll be having a summer school for 2 days. Yes, thank you. Yeah, we hope we passed the time limit today. So let's finish today's session with this. And thank you all for joining me. And I would like to request Dr. Sekhar and Subhash to be online. Others can leave the room. And yeah, if you have time, please join me for another session next week. We'll have a talk on electrochemistry again. Thank you very much. Bye, everyone. Good night.